All right, guys, we are here for day one of quarantined mathematics in statistics with special guest star Micharu, the Siamese cat, which, fun fact, is the most antisocial of our pets, and I don't know why we started with her as our special guest star. But what we're going to work on today is, and there she goes, exponential and logarithmic equations solving for the value of x in their standardized form. Hey again, Micharu. Now, the reason I want to do this, I know we talked about exponential equations a little bit last week, but I feel like it would be worthwhile to go over that again because we just had one short lesson over it. It's been quite a while since that happened, and I just want to make sure we're all familiar with how exactly that process goes. We're also going to talk about the standard form for logarithmic equations and solving for x. And none of the problems that we do today are going to be directly from the packet, but they are kind of in preparation for what we're going to be doing in future days in that packet whenever we start taking the data sets there, putting them into the scatter plots, and actually solving for whatever type of model they are, and then using that model to determine what year this might happen in or what day this might happen in, things like that. So really today is kind of just setting up the groundwork for what we're going to be doing in the coming week. All right, so what we have in front of us here is an exponential form equation and a logarithmic form equation. And we're going to work on both of these with solving for x. So both of these are equations that we see whenever we have a data set that is nonlinear. This one being exponential. This is what we worked on a lot recently whenever we've talked about studying the coronavirus infections here in the United States and across the world, is that exponential growth. And we've created several equations that look like this. And then the logarithmic equation is one that we saw a lot whenever we were talking about data sets like our NWEA scores as we go between kindergarten and high school, and it kind of leveling off. So just to demonstrate that relationship just a little bit, a exponential graph looks something like this, and a logarithmic graph looks something like this. So they're kind of opposites of each other. Now what we're going to do is we're going to create an equation here. I'm going to fill in some variables. Whenever you all have data sets in your calculators, I have a data set here in my calculator. If you want to find the exponential equation for a data set, if you feel like that is what the data set is, then what you do is you hit Stat right here, and then you shift over to Calc, and then you're going to go down to option number 0, exponential regression. And by the way, all this information on how to find stuff in your calculator will be available on your Google Classroom. And then, got to make sure your lists are set up correctly. If you ever, if in your calculator your lists are not what they are supposed to be, for example, my lists were an L1 and L2, then we can change that. Your X list should typically be L1, so you hit Shift and then 1. That'll change it to L1 as you see. And then on the Y list, that usually is going to want to be L2, so you Shift and 2, and then we can calculate properly. So you're going to notice here that we end up with our exponential equation right there, and then values of A and B, and then we have correlation coefficients as well. The values of A and B we can substitute into the formula, which I will do now. So this would be written as Y equals A, which is 13.4, times B, which is 1.248 to the x power. So I believe all of us here can successfully solve this equation for y, right? Like if this data were, which it actually is, this data is the coronavirus infections in the United States, taking it as of to, I believe, March 15th. So in this case, the x variable stands for number of days that have passed, and the y variable stands for number of cases. I believe if I told you guys, if you want to solve for 50 days have passed, what will be the number of cases. All you guys can do that. All we got to do is plug it into the calculator, substituting 50 for x. That's pretty straightforward finding y. We're not going to spend time talking about that. What we are going to spend time talking about is how to find the value of x. So if I wanted to say, instead of on this day, how many infections will there be, I want to say on what day will there be, 6,000 infections, right? So then what I can do is I can actually substitute that in for y. 6,000 equals 13.4 times 1.248 to the x power. Again, this is what we talked about last week in class, but it bears repeating, I personally believe, just because it was new for several of you and it has been a little bit of time. So whenever we have a variable in an exponent like this, then what we want to do is we want to find a way to isolate that variable. Our best way to isolate that variable is to get rid of everything else that is around it. So you'll notice that a 13.4 is with it here, and then it has the 1.248 that is quite literally connected to it. I mean, it's literally the variable for that 1.248. So we can get rid of that 13.4 pretty easily. That 13.4 can just be divided out. So we divide out the 13.4. We take 6,000 divided by that. Let's see. 6,000 divided by 13.4, that's a 7. And we get 447.7. I'm just going to round that up to 448. So we get 448 equals 1.248 to the x power. This is where it gets a little bit unusual, because we don't usually, at least in Algebra 1 math classes or geometry math classes, we don't ever talk about how do we get rid of it, get out an exponent that's in or a variable that's in an exponent. It's kind of unusual for us. So what we actually have to do in a situation like this is we have to apply a logarithm to both sides of the equation. The reason we want to do this is actually to change the base of both sides. By applying a logarithm, we're doing something called changing the base to base 10, and we're able then to do a few more calculations with it. And we have something important called the power rule that is able to be done. The power rule is whenever you take a variable that is in an exponent inside a logarithm, and you are able to drag it around to the front of the logarithm as a coefficient. Now, I do want to clarify, it doesn't have to be a variable in the exponent. Honestly, it's any exponent that's inside of a logarithm you're able to move to the front, but typically whenever we're doing this, it's because it is a variable that we need to deal with. So by applying a logarithm to both sides, we kind of, we do something, like I said, called changing the base, meaning now these numbers can kind of work with each other, as you'll see soon. And then we are able to pick up that exponent through something called the power rule and shift it or move it to the front of the logarithm as a coefficient. It literally removes it from the logarithm and makes it to just be a value that is multiplying the logarithm. That lets us use or work with the logarithm and the variable separately, which will actually make things a lot easier for us. So let's say we want to get that x on its own at this point. Right now it is multiplying the logarithm, and just like any two things that are multiplying, if you want to get rid of one of them, you can just divide by it on both sides, and that will make it go away. So by dividing by this log of 1.248, we cancel it out, leaving x on its own. And on this side of the equation, what we do is we have to divide these. Now, just as a reminder, you cannot simply divide these two numbers. The logarithms in there are very important to us. We have to actually apply that logarithm before writing the number, then close the parentheses to end the logarithm effectively, and then we will divide it by the next logarithm. So 1.248, close that logarithm, and we find out that when we divide those, we get 27.5, or what would round to 27.6. So we get 27.6 is equal to x. So that would tell us that on day 27.6, or what would round in this case based on the context to 28, so on day 28 is when we would see the U.S. hit 6,000 cases. And, you know, if we had more context of the problem, you know, what day was day 1 or what day was day 0, we can figure out, well, what day actually is 28 days later. But, you know, in this case, really, we're just looking at how to get that x on its own. So that is the process for solving exponential equations. All right, so we're going to stop there for today. I know I had mentioned talking about both exponential and logarithmic equations, but I started working on the logarithmic one, and it just felt like a lot to add into one video. So I know for many of you, today's video is just purely review. Apologize if you were excited for something new. I'm sorry. But it was going to be a really long video if I went for the logarithmic stuff, and I thought none of us really want to stick around for like 40 minutes and watch that. So we'll have the logarithmic portion of the video coming tomorrow. And for today, I'll be signing off. You know, don't forget, like, comment, and subscribe. See you tomorrow.